three-phase power and why? And I guess the short answer is that was just the physical arrangement of generators back in the day. And to visually illustrate this, there's a coil, and we'll have a permanent magnet that'll kind of spin around like this. And basically the coils were just physically 120 degrees apart. So let's see, that's about here, and the other one here. Yeah, and you can just have the potential generated here. Positive, negative. So basically that's just it. There's a coil, it's turning around, and there's a permanent magnet. The magnet is spinning around, and the coils are just physically 120 degrees apart. So to go into a little bit of more detail, let's zoom in on one of the coils. And so this is our coil. In fact, I have to remove these because we don't know the direction yet. So using Lenz's law, we'll be able to find the direction of the potential. So I'm going to draw out the magnetic field. Lenz's law and the right-hand rule is going to help you determine how the potential and in which direction it's being generated. So the field line right now, as it looks, the magnetic field vector is going in to the coil. So we take our right hand, okay, so we curl our hands, and which means that the thumb is going to be pointing in to the right here. So the current is going to go in that direction, which means that it's going to come from here and it's just going to go around. Which means that we have higher potential here and lower potential here. As this magnet turns around its axis, it spins around, this magnetic field vector is going to decrease in magnitude, which means that there's an opposite magnetic current reaction in the coil. So as that magnetic field vector decreases in magnitude, there's going to be a magnetic field generated in the coil which is opposing that change. So it's pointing, our magnetic field vector is pointing upwards and it's decreasing, which means that it's the curled fingers are now going to point in the same direction as it does, which means that the current is now going to go through this way. So we now have a change in polarity of the potential. And what this looks like on a time graph is basically something like this if you plot the potential. And this is called a sine curve, sine graph. And since the arrangement is 120 degrees apart, the other sine wave is just going to start 120 degrees after. So I've taken the liberty to plot this. Okay, so here we are on Desmos, and this is a plot of voltage 1. It's, let's just say, magnitude of 120, sine omega t, which is in this case 2 pi 60. And we get a wave that kind of looks like this. The second coil, the potential is going to look something like this, and in the third coil we're going to get the green sine curve. So this is kind of a beautiful geometrical image. This is what it looks like if you would plot all three sine waves on an oscilloscope on all three channels. This is kind of what's happening through the coils. And then it all depends on the load. And the good thing about three-phase power is you can kind of choose how you want to go about it. You can choose the potential across the first coil to run your load if you want. Then you're just gonna get 120 sine, whatever this is. You can also run your load on the potential generated across two of the coils. And I'll show you later what that means. But you're gonna get so the voltage is the potential at one point and the difference between the potential in that point and another point. So if we take the voltage in coil 1 minus the voltage in coil 2, we get this sine wave right here. And as you can notice, its amplitude is greater. And you can see from the first V1, it looks like it's shifted about 30 degrees. So there's so this potential is called line to line. So that's when you're probing two of the coils and running your load on that. You're gonna get a higher potential and a 30-degree phase shift. The voltage across one coil is called line to neutral. So as you can see, it's actually square root of 3 times higher in amplitude. The line to line as compared to the line to neutral. Alright, so let's go back to the drawing board for a second. Okay, so we're back at the drawing board, and what I want to show you is, so what have we done so far? We've seen the geometry that produces these 3 sine waves. We've used Lenz's law to kind of see why the potential changes. And we've plotted the graph so far. So now let's actually run a load on a system like this. And it's usually, there's a couple of ways you can draw this. There's two useful configurations called the Y configuration and the delta configuration. Let's go with the Y just to illustrate a point here. So this is one of our coils generating a potential. We're connecting them in such a way where they're all connected at the base here. And now we want to run a load on this. So you can think of it as one phase at a time. So people usually get confused because it's 3 phases and it's quite overwhelming. And while this is true, if you look at it at just one phase, it becomes a lot easier. So let's just do that. And let's just run a simple load on her, a light bulb or a resistor or whatever. So we already kind of know what's going to happen here, right? The potential is going to go like this, about 60 times per second, or however fast this magnet is rotating around in the side of the generator. Yeah, and so the current is going to go this way for one cycle, and then the other way for another cycle, and it's going to repeat like that, whatever the frequency is. What makes 3-phase so powerful is, let's connect each load to a phase. So this is a 3-phase Y resistive load. Let's just connect this. Like that. Now one phase is going to run. Let's try it out. It's going to go this way to this point. And what you usually do is you connect these points right here. And what makes this powerful is that when you're transmitting this 3-phase power, you only need 4 wires, right? The phase 1, phase 2, phase 3, and the neutral. So you don't have to have a return wire for every single load, which is great because you can just tie this point into this neutral point. And when you're transmitting this to a home, it saves you a lot of wires because so it depends on what you want. If you want line to neutral or line to line, let's just say we're gonna run one single phase load, right? And we have this load in the house waiting for us. Then all we need to do is just pick this point and this point. And now from the generator, let's just draw a generator here. And we got 4 wires out of the generator. Yeah, there's a transformer stage and then to the transmission line. So, and this is nice. And if we want to run a 3-phase application, and we have a load like this in the house waiting for us, then it's the same thing. We just take phase 1, phase 2, phase 3, phase 3, and connect the neutral points back. And this is usually a motor or some kind of, usually these are heavier applications. In your home, you're probably going to use simpler phase, simpler load like this. So that's what makes this so powerful. You don't need, every circuit doesn't need a return wire. You can return everything at the neutral point. You can connect these 2 points together and produce a 0 voltage on this line here. I know at first this can be quite daunting / intimidating. Hopefully this clarified it a little bit. I think I rushed through it a little bit, but this could be a good complementary explanation if you're studying in school, if you're in class, or